Congratulations. Recording's in progress. Would like to recognize Mr. Tyler Doobie as our Engineer of the Year. He was recognized in February at the TSP banquet with other deserving engineers, and we're very excited for Tyler. Also, I'd like to thank everybody who participated in last month's e-week event at the Hill Country Science Mill. It's a great event where we take over the museum and play a bunch of games with kids and just have a real good time. So I want to thank Sharon and Linda for that, and also our new coordinator, Julian Valencia. So looking ahead, we've got our continuing education workshop, which you'll hear more about in a minute. It's going to be on April 20th this year. And so I'd just like for y'all to join us if you could. And so today we are highlighting the Structural Engineering Institute. ASCE offers 9 discipline-specific institutes within our umbrella. And we have 2 operating institutes, EWRI and SEI. And so we want to highlight those groups, and today is SEI's turn. So we're pleased to have representatives from SEI and the leadership here, and look forward to this presentation. So thank you.
All right, thank you, Sam. So we have folks here in person and we have folks with us virtually. So just want to remind everybody how this works, because we haven't done this in a while. For those of you that are attending virtually, we have posted today's program to the chat. If not, we will very soon, so look out for that. You can save that for your PDHs. And we do have some, let's see if I can get one pulled up here. We have these QR codes. So this is the time where you can get out your cell phone and kind of follow along with us at your own pace. And those of you virtually, you can do that on screen. This helps us with things like registrations and sponsorships and things like that, so that you can do that on your mobile device. Before we do get into the announcements, I would like to say thank you to everybody for on the board and the committee and even our branch members that I've worked with over the last handful of years. You know, I've had a lot of support and worked alongside a lot of you to deserve this year's Engineer of the Year award. So I very much appreciate it, and just wanted to say thank you to this group. Sam shared some nice things to say about me, so that was very special day last month. So let's go ahead and get into our announcements. We have our first in-person main event, the Continuing Education Conference, coming up. This is on April 20th from 7:30 to 5. It's at J.J. Pickle campus. And we've got a flyer up here, but I want you to use this QR code to learn more about it. This is where we sign up to register to attend, to sponsor, to be a vendor. That will take you there. We've got some details from the organizers. So as you can see, it's called the Civil Engineering Reloaded, Moving Forward in a Post-Pandemic World. We're looking for about 100 people for this event, so look around the room. It's going to take every one of you doing something for us to achieve that. So that's why I say get out your phone, put it in your browser, and do something with it today. Whether you want to be a vendor, a sponsor, an attendee, all of the above, we'll take it. Tell your friends back at work too, because we need the help. It's creeping up on us fast, April 20th. That's going to be here before we know it. This is an opportunity to get 8 PDHs all in one day and to mingle with your coworkers, your colleagues, and ASCE friends. So we'll be posting the full schedule to our website here soon, but you can see we've got some exciting new topics. There's also going to be a facility tour in the agenda, so you'll get to see a little bit of the Pickle Research Campus. So now I'm going to turn over the floor for some other announcements. First up is Michael Chavez.
All right, thank you all. Yeah, so I just want to recap by thanking you all again for making our winter service event on January 15th a great success. So next up, we'll be volunteering with the Central Texas Food Bank. Central Texas Food Bank is a great organization in our community that helps provide food to the hungry and has been a leader in the fight against hunger in our area for nearly 40 years. So ASCE will be joining the Central Texas Food Bank by serving in the warehouse. Our group will primarily be inspecting, sorting, cleaning, boxing, and preparing food donations for distribution. If you're interested, please check out the Eventbrite link. And if you have any questions, you can email community outreach at austinasce.org for more questions. But to recap, that event will be Saturday, April 30th from 9 to 12 p.m. Thank you.
Thank you, everyone. My name is Austin Mesterly, and I'm part of the CY, the Central Region Younger Member Council, and the YMLS Planning Committee for the Austin branch. And we are hosting that event August 12th through the 14th. And so there's two things we're asking of people. One, to get your younger members registered. It's a great event. It's kind of two different events, so we have two different tracks. So there's going to be a lot of great event speakers and talks included, but also we're looking for volunteers. We have a good backbone of volunteers, about 5 of us, but we could always use some additional help. So keep your name out. If you know somebody, feel free to reach out to me if you're here or send me an email. Thank y'all.
All right, I'm here presenting for YMF. Kaylin Hudson couldn't join us today. Did want to thank everybody for coming out to their joint happy hour. I think there's over 100 and something attendees, maybe 150, along with their creek cleanup, which was recently held. And as mentioned, there's some upcoming events. The Texas Section YMF camping trip will be in the end of April at McKinney Falls State Park. And then the big event, the YMF Charity Golf Tournament, is April 29th at the Avery Ranch Golf Course. If you didn't know, this is the primary way that YMF raises their funds for donations, scholarships, and operations. And so if you'd like to sponsor a team or play, be a good time out at Avery Ranch. Very nice golf course. And then lastly, scholarship applications are due by April 15th for YMF. So if you know anybody who's a deserving candidate for that, please reach out to them and submit their applications. So that's all I have for YMF. Thank you.
Good afternoon. My name is Scott Wallace, and I serve as the communications director with the Structural Engineering Institute. It's an institute under ASCE, as Sam referred to earlier, and our objective is to advance and serve the structural engineering profession. Now, we largely do this through 3 different events. We have bi-monthly, every other month, we have a professional meeting where we bring in a speaker to talk about some current research or some current developments in the industry and such. And occasionally we'll replace that meeting with a technical tour. We've toured the F1 track. We've toured the Waller Creek intake over by the Capitol, things like that, structural engineering related tours. And our third event that we put on is what we call Structural Engineering Talks, SET. You can think of it as kind of TED Talks meets Alamo Drafthouse. We rent out the Alamo Drafthouse, we bring in some speakers to talk about the structural engineering field, but we actually want them not to get into your typical down in the weeds, detailed technical talk, so much as something that's more lively, more philosophical, maybe more cutting edge, but still relates to the industry and all. It's been a lot of fun, and I see some faces here that have participated in it and all. Now with COVID, we've not been able to do it because we insist on doing it in person. and all. And as you can see on the screen, we were originally anticipating doing it this April, but we're postponed that. So you'll just have to stay tuned with our website to keep tabs on that and all, but we still want to put that on. So that's what we as SEI do. And you can contact us, or you can find us on these websites. I've also been asked to go ahead and talk from a different hat I wear, the one I actually get paid to do. I work for Jacobs Engineering, and we're the sponsor today for today's meetings and such. And it really is our pleasure. It really is our pleasure to sponsor this event and in support of ASCE, which does so much for the civil engineering community and such. We were founded in 1948, and Jacobs has been one of the world's largest and most diverse providers of technical and professional and construction services ever since then. We have a staff of over 53,000 people stationed around the world, includes engineers, architects, planners, construction-related folks as well. Our firm combines the vast depth of resources with state-of-the-art technology and innovative management processes and such to deliver projects for our clients. With $14 billion in revenue, Jacobs provides a full spectrum of professional services, both for government clients as well as private clients. As evidence of Jacobs engineering expertise, we are a six-time recipient of ACEC's Grand Conceptor Award. It's the highest engineering award that they give to firms in this country. We're consistently ranked by ENR in the top 2 in things as categories like bridges, highways, transportation, airports, ports, port facilities, things like that. And we just help our clients to provide, to move people and goods across mountains, across the sea, even underground. We do tunneling work as well. Now, as Jacobs, we believe that it's time to really reimagine the infrastructure future, a future that delivers more than for our society in terms of fiscal responsibility, but also the measures of community well-being and public safety, business productivity, quality of life. The ultimate outcomes that infrastructure programs are meant to deliver to bring the critical infrastructure programs to fruition. We work with communities to accelerate their return-oriented infrastructure developments and really make a clear case for sustainable outcomes. Jacobs is more than just the services that we provide. We are problem solvers. We're armed with ingenuity, ambition, expertise. We take on the world's biggest challenges. And at Jacobs, we're challenging today and we're reinventing tomorrow. So thank you for allowing us to sponsor the meeting today. And I'll put on my third hat now. And I'd like to introduce our speaker today. SEI, as was mentioned earlier, has partnered with the ASCE today to bring the speaker for this meeting. And we're pleased to bring Dr. Jeremiah Fasl. He's an associate principal at Janney, Elstner Associates at WJE to most of us. Among other roles, Dr. Fasl has been the chair of ACM Committee 357. That's the Offshore and Marine Structures Committee. He's a voting member on ACI Committee 348, the Structural Reliability and Safety Committee. And he has interests in structural reliability, as you can imagine, structural stability, civil infrastructure, structural health monitoring, and rehabilitation. He's going to bring those all together for us today. He's going to talk about the Barbours Cut Terminal, container port wharf. I'm going to press enter here and see if we get to the, and I'll let you take it from there. But anyway, it's the container port wharf that is operated by the Port of Houston Authority at the Barbours Cut Terminal. It was recently upgraded to support the larger 100-foot gauge container gantry cranes that unload the big Panamax ships that are coming through the expanded Panama Canal. These are the biggest of the big. If you've ever been down there, they are some enormous loads and some big cranes are needed to handle that. His presentation will talk about the rehabilitation of the wharf, which also involved in-depth assessment, service life evaluation, and repair design. The rehab design that was developed to accommodate the larger gantry cranes featured demolition of a portion of the existing structure and construction of 2 new crane beams to support the crane rails as well. The design of the new structural elements featured several challenges, which Dr. Fasl will get into for us. So please welcome Dr. Jeremiah Fasl.
All right, thank you. Glad to be here with all of you, as well as all the people virtually. It's a very exciting project for me to present on. I would say it's one of my favorite projects that I've done in my career at WJE, mainly because of how big all the loads are, the structure is, the cranes are, as I'll talk about a little bit later. So Barbours Cut Terminal, as Scott mentioned, is one of the container ports operated by the Port of Houston Authority. And our scope for the project was purely structural. So I guess I'm gonna first figure out how many structural engineers I have in here. You raise your hand. We have a few, okay. So I'm gonna be talking a lot about structural, but I'll try and open it up to other things. So if you have questions, feel free to reach out. Our scope was to do an assessment and then to pair that with service life modeling to figure out what repair strategies were most appropriate for the structure. And then the big part that I was involved in was the retrofit design to handle these bigger loads and cranes. The Port of Houston's been around for a really long time. It started out where things were barged in Galveston and then taken along the Buffalo Bayou ship channel. A couple hurricanes knocked out Galveston infrastructure such that they really wanted to dredge that bayou. And that's the ship channel that we see today. So all that was done in the very early 1900s. Some of the structure that Port of Houston maintains today is from that original 1900, 1910s construction. So City Docks 1 and 2 at the Turning Basin are some of the examples of structures that have been around. Today, the Port of Houston rates as the busiest US port in terms of foreign tonnage and overall tonnage. And this was just recently, I was looking up, because a couple of years ago they were second. So a lot of the resources has put them to the top. In terms of container ports, they're a little bit lower. I think they rate as number 5 or number 6, but it's something that is increasing as they expand their capabilities. So this is just a map of Houston, Galveston, and the Port of Houston infrastructure ranges over that entire box that you see there. So if we zoom in a little bit more, they have their turning basin, which is one of those early 1900s at near the downtown region of Houston, all the way to the container ports that you see on the right-hand side. And they do everything between cargo, containers, as well as liquid and bulk. I think liquid accounts for most of the tonnage of material coming through, but containers is increasing recently. And so I'm going to be talking about this area of Barbours Cut. Barbours Cut features 6 terminals. They are each about 1,000 feet long, and they were constructed between the 1970s and the late 1990s. Barbours Cut 3 is going to be my focus. We were involved a little bit on 1 and 2. Jacobs was, I think, the lead designer at that point. But my project I'm going to talk about today is 3. This is part of Port of Houston's redevelopment of this entire wharf to handle those bigger ships coming through the Panama Canal, those so-called Panamax ships. Barbours Cut 3, constructed 1978, 1980s, and each features 3 different units, each of them 333 feet long. So there's an expansion joint in between each unit to account for that total berth length of 1,000 feet. The original structures were designed for a variety of loads. They have the gantry cranes that you see in that bottom picture. The gantry crane back then was 50 feet gauge. So that just means the distance between the crane rails, and a variety of self-weights, gravity self-weights that we're going to talk about. For live loads, they had a 800 PSF live load, so much bigger than anything I've designed for previously to this, to account for the stored materials on the structure. And then going into mooring and berthing, I'll get into that a little bit more. That's something that was new to me for this structure that accounts for some pretty large loads as well. So the existing structure is actually pretty simple. It features drilled shafts, as you can see, that support a flat slab on drop panels. So very simple two-way behavior. And then on top of that slab, you have a fill with a pavement, and that just helps redistribute the load for these large, heavy loads that we're talking about. Along the front side of the wharf is the bollards, and those are devices that help hold the ship in place due to wave action and wind action. And then a fender system to protect the existing structure as the ship is coming into to dock. Along the backside, there's a bulkhead and tieback and whale beam to just hold back the soil. So overall, pretty simple structure. And then for the original, they had crane beams highlighted here that are 50 feet apart. So why is the Port of Houston interested in rehabilitating the structure? Well, part of it is just due to its age. So it's been there for over about 40 years, and it's in the Gulf Coast. We all hopefully have been to Houston and know how humid and hot it is. Well, those combined with the chlorides that are in the water combine for the perfect opportunity for corrosion. So this is a picture from another structure at the Port of Houston that's seeing some corrosion of the bottom reinforcing bars. All that is, concerns for the extending the life another 50 years for the structure. And then the other bit that Scott highlighted was just the expansion of the Panama Canal. And this is where a lot of structural design went into figuring out the best ways to rehabilitate it. This whole project is just a continuation of the work that was done on 1 and 2. But where they were in, the port was interested in actually defining service life for 50 years. The expansion of the Panama Canal means bigger ships, taller, wider, longer, and they need larger cranes that can support that. And so just to show you that scale picture, we have the original cranes, the green ones on the left. And so again, they were designed with a 50-foot crane rails in between the rails, whereas the one on the right is 100 feet, so it can extend further, it's taller, and can carry bigger loads. So the design team for Barbours Cut 3 featured BGE, who was the lead civil designer. They were the prime for this firm, and they were handling all the utility, water, as noted here, and some redevelopment that was occurring in the container area behind the wharf. We led the structural design and retrofit, and we worked quite a bit with Lyman C. Rees on developing the geotechnical aspects of this project. So the overall concept for retrofitting and repairing this structure was to take these original crane rails, which are those blue arrows, and just adjusting them a little bit. So we're going to move one of the crane rails inward a little bit, and then the other one's 100 feet away, and then cutting off the front part of the wharf and redesigning some structure to directly support those crane rails. So all the items in orange are new structure. And so we're relying on new drilled shafts that directly support that crane rail, but we're also integrating that new structure with some of the existing structure there. So you have the A grid line, which is an existing drilled shaft that's connected into a new crane deck beam. And you have on the backside a connection to the existing structure as well. So much bigger loads, 100-foot crane gauge, and then a design criteria of 50 years. So our scope, just to kind of summarize it again, was to assess the structure, figure out if corrosion has been occurring, if it has, how do we mitigate it, and then doing some service life modeling to figure out the best retrofit opportunities, and then design for the new structure. So I want to talk first about the existing wharf and what we observed. We did 100% visual assessment of the structure, and because it's in water, we're in boats doing that assessment. And we did a lot of non-destructive and destructive techniques to evaluate both the corrosion as well as just any inherent structural concerns, defects in the concrete. So that's why we utilize the chloride analysis, the concrete petrographic analysis, and compressive strength. this is just us in doing our visual survey, moving along. There's only one area that you can walk on along the backside of the wharf, and that's where the bulkhead is, as you can see on the right-hand side of that picture. But otherwise, the majority of the wharf you can only see from boats. In addition to the visual survey, we did half sail potential, and this just gives you an indication of underlying corrosion that may be occurring. And so it can give you a characterization of low, medium, or high risk. And this is a non-destructive technique where there may not be indications of other distress. We also did some corrosion rate measurements, and the intent of these were just to understand how it correlated with our service life models. So we did this at various elements throughout the structure. And another technique is service resistivity. And it's an indication of permeability of chloride ions. So it kind of gives you an indication of how good the concrete construction was originally. In addition to those techniques, we also use GPR to do our cover depth measurements. There's quite a bit that is needed for the service life modeling. And so these are just incorporation of the actual cover. And then you can see that we had to use unique techniques to capture cores. And so here we're shown just extending over the boat, but also having to use some scaffolding to get the cores so that they don't drop into the water. Overall, if I just summarize what we saw really quick, the deck had a little bit of cracking in it. It's well above the water level, so it doesn't see the same exposure. And so all of our NDE indications were showing that this is a low corrosion risk. We had a little bit of efflorescence, but not too much. But you start going down lower towards the water line, we saw a lot more corrosion damage, a lot more potential for that risk of corrosion. The whale beam, as you see in this picture, there was corrosion. I have a better picture later on, but beyond that, the bulkhead wall, these are all within the splash zone and see a lot of wetting and drying. And then finally, the drilled shafts, you can see the swallow that was observed, a lot of risk for corrosion. And so being able to take those measurements, take those readings, and really do something with it was where the service life modeling came in. And this is to help us refine what elements needed the repair and which elements were okay as they were. And so we used the FIB Bulletin 34 for our evaluation of the service life model. It's a probabilistic approach that uses your data that you capture in the field, so your cover measurements, your chloride diffusion rates, your chloride profiles, and then extrapolates that to predict the service life. Part of doing those calculations, you have to define what end of life actually means. And so we had to work with the Port of Houston to see how much corrosion, section loss were they comfortable with to require later repairs. So this is just some of the data that we collected while we were doing this assessment. These are the chloride profiles for different cores with depth. And you can see that in the tidal zone, you're getting high values right at the surface, which is expected because you get the water and splashing from the chlorides. And then as you go deeper, it takes that concentration is going down. And so we fit curves to represent that so that we could use it for our models. Just because it's a probabilistic approach needs an actual number as opposed to a bunch of data points. So these are some of the curves that we used. We also defined different regions, exposure zones on the drilled shaft. So we have zones that are submerged, tidal, splash, and atmospheric. And you can see how the chloride profiles levels kind of varied with its exposure zone. So in that tidal and splash zone, we expect to see the highest, which is what the data indicated as well. This is the end of life criteria for all the new elements. And for example, our new concrete elements, the Port of Houston wanted no more than corrosion initiation 10% of their elements. And so this was working with the Port of Houston to define this. This is very project specific, but this is where we could then go and estimate our remaining service life and look at where we are today and where will be in 50 years to see which elements require mitigation, repairs, and which ones can go for another 50 years. And so you can see from this curve, these are looking at existing elements. Those orange lines represent atmospheric zone, and going 50 years into the future, it's going to be less than 10% damage. So that's an example of something that doesn't really need to be repaired, whereas the things in the tidal and splash zones will be well above that, and currently are, is based off the corrosion and damage that we were seeing already. So we were using the service life model to calibrate our models, or using our field data to calibrate our models and then estimate forward. So just wanted to quickly summarize some of the repair techniques that we use to mitigate the damage. This is an example of a delamination. So it's at the initiation of corrosion and it needs to be addressed. We used just a typical partial depth repair. This is something that you might see in ICRI or some other ACI documents about how to do, but it involves demoing out all the unsound concrete, getting behind the bar, cleaning the bar, and then putting some corrosion inhibiting material on the bar. And in this case, we're going to also install some galvanic anodes to mitigate future corrosion. So those are a way of providing localized corrosion protection for the repair so that they can last longer. Where there was more significant damage, such as those spalls that we had a couple pictures of, instead of just doing local repairs, we also wrapped the concrete with these cathodic protection jackets. And these cathodic protection jackets feature a bigger bulk anode kind of towards the bottom. And those provide the cathodic protection such that the zinc gets consumed as opposed to the corrosion occurring in the reinforcing bar. So it's a way of, ensuring that you last the 50 years that you want to, and you just have to design all those features together with your repairs. And this is just an example of what that looks like. The jacket is extended 3 to 5 feet above the water just to represent that splash and tidal zone that's the most critical for the drill shafts. This is a picture of the bulkhead whale beam, and this is where we saw pretty significant deterioration in that bottom mat of steel. So you can see that crack, the lamination that's occurring there. As a result, we did the concrete repair that we talked about. That's what the pictures on the left are, is to remove that unsound concrete and cast it back. But to provide further cathodic protection, we detailed zinc sprayed applied coating to be applied to it to provide cathodic protection. So the zinc gets consumed as chlorides penetrate rather than the steel itself. And so this is another mechanism of providing long-term repair. So now, kind of talked about the existing structure, I want to get into what I'm most excited about, which is the rehabilitation design. The rehabilitation design is the strengthening aspect of the project. And so it's where we installed these, or designed the new orange elements that you see there, which are the crane beams, the frontal beam where those fenders and bollards are located, and then some connecting pieces, the deck beams and tie beams. Just talking about our loads first, just kind of get a sense of how big this project is. We had live loads of 800 PSF. We had HS 25 vehicles for 5 lanes over the width of the wharf. So it's very similar to a bridge in that sense. And all these loads are moving. So you have container lift trucks and cranes that can move anywhere on the wharf. But the big one for me was the ship to shore cranes. And so the ship to shore crane are those 100-foot gauge cranes that you see here. And the picture on the right just is trying to show you the scale of a person or truck next to the crane. And you can see how much bigger those cranes are to reach out and get the containers off the larger ships. So the loading on the cranes can be simplified into 16-point loads, having 8 on one side, a bigger spacing, and then 8 more. Does anybody want to guess what your total crane load might be? Nope. A lot? Yes. Yep, the big cranes. Yeah. Just want to throw out a number. Anybody? 200,000 over here. 2,000 kips. And you said 200? Okay.
2,000 megapascals.
Megapascals, I can't do that conversion. So you're close. It's in the range. So 4.7 million pounds over that 80 feet. So quite large. The individual wheel loads are about 300 kips per wheel. And this can move anywhere along the crane rail, along the 1,000 feet of wharf. So much bigger than anything I've designed for previously. And then in addition to all those live loads, we have mooring and berthing. And so the mooring loads are to keep the ship in place. And they get ropes attached to these yellow bollards that you see in the pictures on the right. And it's just as waves hit it, the waves hit the ship or wind hits the ship, it keeps it in place. Whereas the berthing is just to help protect the structure. The fender design or the berthing design is all energy based. So that was something I hadn't done before. It is completely 1/2 mass times velocity squared. So you just define your mass, define your velocity that you're going to design for, and then you figure out the energy. There's a couple of correction factors if you're going at a slight angle or what types of waves, but that's essentially what you do to design fenders. Get your energy and then figure out a fender that can support that energy. So that was actually pretty straightforward. The bollard design is a little bit more involved because it takes your ship and you apply wind in any direction all around 360 degrees and apply some waves and see what the reactions that need to be there to hold it in place. And so for this example, it's 280 kips of a horizontal line reaction that needs to be resisted by the bollard. Lyman C. Reese performed the geotechnical investigation. They relied on previous borings at the site and then also did 4 new borings. They performed all the slope stability, the rapid drawdown, but they really defined the drilled shaft analysis that we used in our evaluation. The soil in Houston at Barbours Cut is mainly clays, but it also does feature some silty sand regions, and all that was accounted for in how they got their axial capacities and lateral capacities. So they gave us these designs that we could use, but they also defined some springs for soil structure interaction. And those are springs that we had to bring into our model and evaluate, but which allowed us from some structural efficiency, as I'll talk about. So the model that we created was a half a unit, so half of 333 feet. We're relying on some symmetry to reduce our runtime, but it considered all the loads I just talked about previously, all the live loads, mooring, berthing, crane rail loads, and et cetera. But we had to incorporate those soil springs into the drilled shafts. And so they vary with depth and create a nonlinear problem that needs to be solved. And then we focused a little bit on how that new structure is connected to the existing structure. And the next slide is going to highlight that a little bit more. And then the final thing I'm going to talk about is just the strut and tie models that we had to use for some of the bigger crane elements. So the soil structure interaction and soil spring interaction is shown here by showing how load is shared amongst drilled shafts. Line A2 is a new drilled shaft line, and it features our new crane beam along the water side. Whereas line B is existing structure, and line A is existing drilled shafts, but new structure on top of it. And so if I just apply a uplift force to this particular structure and see how much of that load goes into adjacent elements, you can see that only about half of the load is carried in the immediate vicinity of that load. So that allows the drilled shafts to be designed for a lower force, which means they don't have to be embedded as deep. The outcome is that we have to design some of the other elements to be stronger to be able to carry the load. So the line A2, the line that's directly seeing that force only sees about 70% of the total load, whereas 12% gets passed to the line A drilled shafts and about 20% passed to the line B drilled shafts. The part that we needed to model and make sure that we got right was where the line B and A2 moment releases and shear releases were done properly, because we're providing just a dowel between the existing drop panels and the existing deck and the new crane beam. And so we had to make sure that we were able to resist the moment that gets load transferred to line B. The big elements that were new were the crane beams, and those waterside crane beams are 4.5 feet wide by 4.5 feet tall. And they're supported on drilled shafts that are spaced about 10 feet 9 inches on center. Due to the clear span, they are defined as deep beams in ACI. And so ACI would tell you, you need to consider nonlinear strain distributions for analyzing them. So no longer just simple moments and shears, it's about carrying it with, as I'll talk about, strut and tie. So this is an example of what load transfer in a deep beam might look like. If you focus in and apply a load is going to extend diagonally to your support locations. And so these are struts in terms of strut and tie vernacular. And then you need some tension force to kind of hold it all together so that they don't separate. And so the red lines typically represent your compression struts and the blue lines represent ties. And this just follows what you'd expect to see in a deep beam. Well, one way to evaluate those is to use strut and tie modeling, where you create a truss of concrete elements, where your concrete elements are called struts, the steel elements are your ties, and your nodes are just where load concentrates. We implemented strut and tie for this particular wharf, and we got good design results, but there were some challenges that we had to overcome. Not often are you dealing with strut and tie models where the load is moving. And so having to create multiple models to envelope those results was challenging. But kind of highlighted a little bit about those flexible supports when we were talking about how load is shared. Well, it also impacts the strut and tie model. So you can see here, if a strut and tie model had pin supports where everything's really fixed, it's just going to deflect in between the supports. Whereas if you add flexible supports, then things are going to globally deflect in between. Well, the outcome is that effectively increases your span length. So they need the crane beams need to span further and need more reinforcement. But they're no longer just statically determinate anymore because of those springs. And so we had to be conscious of the stiffness that we chose for our cord members to make sure that we were getting realistic deflections. So we ended up using the transform section properties of a concrete beam to provide our stiffness. And just comparing the two results, if you used pin supports and you went to flexible supports, you need twice as much steel for those flexible supports as the pin supports. Well, all in all, we designed these with number 10s top and bottom, and then had to have stirrups there for a little bit shear, a little bit of just the detailing requirements of strut and tie, as well as some torsion that gets induced from all the interactions that occur. Now, the other big reaction that I want to talk about is the tie downs. So previously we were talking about 300 kips per wheel load. Well, the tie down for hurricane levels is a single point load of 2.3 million pounds. And this is a load that's applied when the cranes are locked down. So anytime the wind gets above 55 miles per hour, the cranes have to go to specific locations on the wharf and get locked in. Otherwise, they could potentially topple over. Otherwise, during normal operation, they're going anywhere along the length of the wharf. So each corner will see 2.3 million pounds for that 150 mile per hour wind event. Functionally, they get tied down through clevises, which is the picture on the right. So that's actually from the crane, and they get tied into these pins that rotate up on the crane girder. There are 2 pins, one on either side of the crane rail. And as a result of them being outboard of the crane rail, we had to widen the crane beam in those specific areas. Well, that creates a challenge from a strut and tie perspective. We have a picture on the left with just our elevation and our section view on the right. Imagine pulling up with 2.3 million pounds. Half of that goes to either side. Well, the first strut and tie is your typical strut and tie that takes the load to the drilled shafts. But you get a second strut and tie model that needs to be considered, where you're taking load from outboard of the drilled shafts, outboard of the crane rail, and trying to bring it inward into the centroid of the section. And so what the second strut and tie model tells you is what the horizontal force is at the bottom of that section in the right-hand picture. And you can see that if you actually looked at it from 3 dimensions to see we're trying to get that force that is trying to hold the section together. Had to put a lot of steel in there, 14 number 11, 6 number 10s along the top. But the hairpins, the 6 number 8s, 3 on either side of the tie down, is what comes from that 3-dimensional model. So a little bit of challenges. Hadn't seen any of these before, but it was very interesting to kind of work through the different aspects of it and handle very large loads. As you can imagine, there's a lot of steel, but there's a lot of conflicts potential. And so we had to create different detailing diagrams to understand where they're going to have conflicts and put these on the drawings for the contractor so that they are aware, hey, you're going to be concerned about these candy canes, right? They're going to be an important part. But the contractor was really good with doing mock-ups early on to make sure that they got everything correct. And this has been constructed, so they did get all the steel in there without any problems. The last thing I'm going to talk about, and then I'll be done, is just the bringing together that service life modeling that was talked about before into a corrosion protection plan. And the corrosion protection plan was just something that was discussed with the owner about what are the best techniques to design the concrete members for that 50-year service life. And once you develop that corrosion protection plan, whether it's putting in galvanized steel or it's just increasing the permeability of the concrete, once they decide, it has to be incorporated into the construction documents. And so that's the drawings as well as the specs, and requires that coordination between the people who are doing that, as well as me, who is doing the analysis and the repair drawings. And it also required a lot of upfront communication with the contractor to say, this is our intent, this is what we're trying to achieve. And just to show how that was done, I'm going to highlight these concrete specs. Our concrete specs were performance specs for different elements, like this is what we're trying to achieve, and how they varied with the different elements. So I'm just going to highlight the drilled shafts that are along the water side in the water, and the concrete, just your typical crane beam. So they had slightly different water cementitious material, so it's 0.4 and 0.42. And they had different cement requirements because the water side crane drilled shafts are in water. And so they need the higher sulfate resistance. Different cementitious material, cementitious material, supplemental cementitious material contents. We needed higher permeability, reduced permeability in our drilled shafts because of the exposure to the chlorides. And then we wanted to see that impact from test results. We also had some bleeding restrictions because of previous problems at some of the other locations, as well as a max drying shrinkage. And this max drying shrinkage was related to our service life model to ensure that 50-year service life. So hopefully you've seen why I like this project so much, due to its scale and a lot of different intersecting elements. It required that thorough assessment up front to understand what's the condition of the existing 40-year-old structure. But it also required a lot of analysis because of such large loads and interactions, and how everything kind of fits together once you develop those service life models and can figure out the right solutions. well, it needs to be implemented in the design drawings as well. So with that, I will open it up to any questions. Yep.
So it looks like you cut off the front of the pier.
Yep.
And then work behind the bulkhead. Did all the load resolve into those two locations? And how did you connect it? Because it doesn't look like the spacing of these built shafts were the same as existing.
Okay. So the question was related to, we cut off the drilled shafts or cut off the structure, right? Which is what we're trying to show in this picture. And so all the new elements are orange. Okay, and can you continue your question?
So is all the loads, those large loads, resolve just into the new structure? How did you tie it into the existing?
Yeah, okay. Yeah, so the question is all the load going into the new structure, or is some of the load going into the existing? And if some of the load is going into the existing, how did you do that tie-in, right? So along the land side, the left side of this plot, everything is going into the new structure. And there's no water there, so they're not extending 60 feet unsupported. And so those drilled shafts in general are going to be much stiffer. Whereas the pictures on the water side crane beam is actually getting shared between multiple elements. And that's where I was showing some slides later on that showed that sharing effect. Okay, so this is that scenario that you're talking about, where line B is existing, line A2 is new, and line A, the drilled shafts are existing, but the structure is new. So between line A2 and line B, we had to put dowels that made a connection. And so if it's just a single road of dowels, we're just relying on shear transfer to get load from A2 to B. But there are some drop panels, and there we had two sets of dowels to create a moment couple. And then there we're getting some moment transfer that helps transfer load over.
Your new drilled shaft spacing was the same as the existing?
Yes, but just they're offset a little bit, but yes, they along the water side, everything is very symmetrical and constant.
So your deep beams, did you have to add concrete to transfer that load? Because then they wouldn't line up with the transfer of the...
So the question now is, for the deep beams, did you have to add concrete to make that happen? And when we evaluated the deep beams, the strut and tie model, we were actually only considering the line A2 drilled shafts. And the reason for that is because we were designing just the steel for those. So we were providing a mechanism where there was enough steel that load could be transferred as needed between the drilled shafts.
So they're very short brace.
Yeah, exactly. And that's where those there's some deck beams that are not shown in this picture that are bracing it laterally. And then we have the dowels to the line B sections, the deck that is also bracing it.
One more question, sorry to monopolize it. How do we get those drilled shafts in between all those tie-backs?
So yeah, so on the land side is, okay. So the question is, how did they get the new drilled shafts along the land side and not hit the tiebacks? Part of the scope was to expose those tiebacks before they did the drilled shafts. So that's part of the scope from the contractor. To understand where those tiebacks were better, we did some surveys beforehand, because you can see where the tieback is expected to be along the bulkhead that you can walk along. And so you can do some surveys. And so BGE was the one coordinating that, but they did some surveys to predict where those were. And then we spaced our drilled shafts along this land side to avoid those tiebacks. And so we actually didn't have any problems during construction with that. Yes.
I have questions kind of about the water levels as y'all were doing your design. So can you talk a little bit about that? Like, is high tide an impact here, high tide, low tide, the water level rising, storm surges, things like that? And if the deck of the structure is lifted, is it pinned under? I know you mentioned that about the cranes.
Yeah, so the got a question related to the water levels and how that might have influenced the design, right? So the high tide impacts the depth of some of the repairs. And so that kind of shown a little bit on this area where we had to create exposure zones where we expected the tidal region to be, and then the splash region above that, because we're expecting to see higher chloride levels in those areas. And so that may impact how we implement repairs. And so from that perspective, that was considered in the design and implemented. The storm surge question is not something that I explicitly considered. I would need to think about that a little bit more. I'm not sure that, so I don't know actually what the highest value of storm surge would be if it would get above the deck, because these are 15 feet above normal water line. So that would be a pretty significant storm surge. So I would suspect that we do have enough tension that the deck's not just going to lift off, especially in the areas where we have the tie downs. We have significant there, but I don't suspect it elsewhere either, just because you have the deck, you have the fill on top of the deck, and you have pavement on top of that. So, all right, I have multiple questions. We'll go first to Tyler.
Was it difficult getting the drilling equipment in there to drill the new shafts with the existing shafts already there?
Yes, and I don't have a picture of that, but the contractor who did Barbours Cut 3, sorry, I forgot for the internet audience. The question was it difficult to get the drilling equipment in there for this project? And the answer is yes, but I think all of that was with Barbours Cut 1 and 2. The same contractor who did Barbours Cut 1 and 2 also did Barbours Cut 3. It's going to be a problem with the next couple of wharfs, 4, 5, and 6, because the soil is getting worse and worse as you progress from the right side towards the left. So as you go from 1 to 6, it's getting worse. And so they have limits as to the maximum length of that they can drill. And that's right around 200 feet long, which is right on the level that we might need to go to for Barbours Cut 6. So we're kind of working with the contractor on that to potentially go to bigger drill shafts to compensate for the fact that the soil is getting worse. So.
I have a question from Gary K. online. Gary asks, did you use polymer coated rebar? If not, why not?
The question was, did we use polymer coated rebar? Yes or no? We did not, because we didn't need to with our corrosion protection plan. So to go that 50-year life, we didn't need to utilize that. Instead, we designed the concrete to be less permeable and higher covers and things like that. So we did a more traditional approach as opposed to going with polymer coated rebar. Okay, go there first and come back.
Couple of questions about the drill shafts. What's the depth of penetration of the new shafts versus the old shafts?
Yeah.
And was the drill shaft construction classified as over water or over land for emission purposes?
So 2 questions. One related to depth of the drilled shafts, the existing versus the new. The existing drilled shafts vary as you go from front of the wharf to back of the wharf, because the soil is also, the dredge line is varying. So right at edge line A, which is towards the front of the wharf, I think that they were 100 to 120 to 140 feet long was the original. And then our new drilled shafts needed to be 140 to 160 feet long, if I'm remembering correctly. So I'm going based off of the elevation, the mean water elevation that we use, and that was like 140.
Top of the shaft or from the dredge line?
That would have been from the water line, and so then if you consider another 15 to 20 feet for where the top of the drill shaft will be. So we were in the 180 were our longest drill shafts for this project. And the, I would say that the original structure was probably in like the 130 to 150 total length. So. Austin, do you have a question?
I'm glad you stopped stuff because did you determine those?
Oh, sorry. You had a second question and I did not answer that. Sorry, Austin. So your second question was it considered overwater or overland for emission purposes? I do not know the answer to that. They were technically still on dock when they were doing the drilling, but the Port of Houston does have specific dredging requirements and things. I did not get into the specifics of that, so I don't have an answer to that. Sorry. All right, Austin.
So the kind of tidal zone splash zone was determined on kind of existing data.
Yeah.
Y'all were seeing.
Yep.
Over that design life of the next 50 years, do you expect those to rise or fall, or was that different?
So the question is, we have these tidal splash atmospheric zones, and will those vary with time? The Port of Houston infrastructure has subsided over time, and so things are going down deeper into the soil. It's been a small amount over the last 50 years, but it's noticeable. And so we did take that into account in our design. And so we extended, if we did some jacket repairs, we extended a little bit beyond just to kind of protect the repair strategies that we implemented.
What about like rising levels, water levels? If it shrinks a little bit with the water level.
Yeah, the splash zone will go up and everything. What the Port of Houston was interested in doing was addressing immediate concerns for these, and that's why we jacketed some of the jackets, but not every jacket out or every drilled shaft out there. So they kind of saw our service life model results and then used that to decide what they were comfortable with repairing. And so, yes, the splash zone could keep rising and affecting more of the concrete. And I think that they'll just have to address it at a later date.
All right, well, Dr. Fasl, thank you very much for
Yep.
being here. We have a speaker appreciation gift for you. We haven't been able to give one of those in so long, so that's a Yeti-like tumbler. I hope those are still cool.
Oh, they are.
So thank you very much. It was
Yeah.
a great presentation.
Thank you.
And now we'll turn it over to Sam to close us out.
Thank you, Tyler. Thank you, Dr. Fasl and SEI. Thank you all for your attendance today. At this time, I'd like to ask our membership chair, Griselda Quintero, our total membership today.
Yeah, today we had 30 people show up in person and 23 left out and virtual.
All right. 53 participants today. All right, well, I appreciate it. We'll see you back here on April 19th for a joint presentation from the City of Austin and TxDOT on the I-35 Capital Express project. And we're going to have it here. So we're excited to have a home and a great venue to meet at. And so with that, this meeting is adjourned. Thank you.